Welcome to Chapter 2, Lesson 1. In this lesson, we will talk about Ton's memory layout and TVM operation. So let's start with the unique feature of Ton that is called cell. The interesting thing about Ton is that all the data structures in the entire blockchain, within your own smart contracts and in all the standard data structures in the consensus protocol, they're all built on top of cells. So what is a cell? Cell is a small building block of the entire data structures in Ton blockchain. Each cell has up to 2023 bits of data and up to 4 references to other cells. And this allows you to use cells to build arbitrarily complex and nested data structures. And this is really the only data storage that you have when you build your own contracts. This means that you cannot simply allocate arbitrary array of bytes like you could do in, for instance, Ethereum or in your regular computer. You have to put your data and lay it out in the tree of cells. And then this data is transmitted and stored in a format called bag of cells. And this is something that is familiar to the users of Git. In Git, you know that every object has its own unique identifier, and there are deduplication mechanisms that allow you to effectively compress all the individual objects in one repository. And this is pretty much how the cells work in Ton. Every time you transmit a tree of cells or a collection of various cells, all of their nested cells, they're effectively represented in this bag of cells with all the necessary deduplication if needed. Now, this storage model is obviously giving some challenges to the developers, because now you have to split your data in those chunks of 2023 bits, which is slightly less than 128 bytes. And you have to think how flat or how deep you want to build the tree of your data. But the cool result of this design decision is that the entire state of the blockchain can be effectively Merkleized, which means you can create the Merkle proof, the cryptographic proof of any portion of the data in the blockchain at any state of it. This is crucial when you scale out to a large a system with multiple shards and separated validator groups, and you need to verify that some groups behaved correctly and didn't break the rules of the system. And this is where the effective compact Merkle proofs are necessary to prove any misbehavior by any participant in the system. And so building the entire Ton blockchain out of the cells really helps with that. Now let's take a look at how this comes together during the execution of a smart contract. The storage of a smart contract is represented by a cell. And if you need to store more than 1023 bits of data, then you could use additional cells that will be connected to it via one of the 4 references. And so on, you can build arbitrarily large state of the contract. When the contract receives the incoming message, the validating node instantiates TVM, which is a special purpose stack-based virtual machine that is designed to execute Ton bytecode. This virtual machine is loaded with the current state of a contract and its current code. And both the state and the code are stored in the cells. Now, all of this data is loaded up in TVM, and the job of TVM is really to just go through the code, execute it, verify all the network rules regarding gas costs and the correctness of all the operations, and in the end, return either an error or a new state of a contract that will be stored in its place. And also, there is another type of data that is emitted as a result of TVM work, is the list of outgoing actions that are typically the outgoing messages that the contract wants to emit and deliver to other contracts. So TVM is instantiated for each message, and it's a pretty lightweight virtual machine. In the entire blockchain, the only data type that you have is a cell. Then in TVM, you have a slightly more types of data that you could work with. And most importantly, you could work with cells, and you could work with integers. And another core type of TVM is the 257-bit integer that allows you to represent wide range of integers suitable for cryptographic work and for financial operations. All the data types that TVM works with, integers, tuples, and cells, could be read by the code in the contract out of its own storage, manipulated on the stack, and then the new storage could be created with the output action. If the execution was successful, then the TVM is unloaded from memory and the new state of a contract is stored in its place. Now, let's talk about the memory layout available for the contract. So as you noticed, the only available option for your memory layout is a tree of cells in a contract. So how do you store things like lists or dictionaries or sets in the system? Turns out it's not very trivial to do because the cells are very compact and they form a tree. To help developers with this, Ton comes at the level of TVM and also at the level of FANCI, the higher level language, with tools that help you work with hash maps in a more effective manner, and they use cells as the underlying implementation. So the hash map is effectively a tree or a prefix tree that stores your values where the path to a tree forms the key to it. So this gives you a logarithmic cost of accessing your data, and the built-in tools in the TVM give you a usable interface to iterate over all of this data or do insertions and deletions to that data. However, you should note that the key to scalability in Ton is to limit amount of work that is done in any single place, because Ton is scalable across contracts, but each individual contract is not scalable out of the box by itself. So if you design a system where you have a large hash map, say you have millions of users and you put millions of records in your list, then that would be a bottleneck for your application, because all of these transactions would have to go through this contract. And also it would be quite expensive in terms of gas fees, because by design in Ton, every time you have to jump from one cell to another by reference, it's called unpacking a cell. This is a quite expensive operation. And there is a good reason for it, because if you have a long chain of unpacking the references, then it means that anytime you want to prove anything about the state in the network, your Merkle proof would have to be equally large. And to make sure that those proofs are reasonably compact, there is a high price for creating those nested cells. So what do? First answer is that this is totally acceptable to have nested cells for a small amount of data. So for instance, if you make a system with very few participants, let's say a multi-signature contract, then you can store this data in your hash map right into the contract, and it will be reasonably small. If, however, you're building a system with millions of users, then you should think about using tokens to represent users' participation and avoid storing the lists of these users in your contract altogether. Finally, cells have a built-in deterministic hashing scheme that allows you to identify uniquely any cell in any part of the tree, and this is used both for data deduplication and compression. So for instance, when the contract runs out of money to pay for the rent, its current state is offloaded from the blockchain. It's completely forgotten, but the network still stores the hash of the storage cell. This means that the user could come later and provide the original tree of cells that matches this hash and reinstantiate the contract. And this way, the state of the contract is fully preserved by the hash of its entire storage. So in conclusion, at the base of the blockchain, everything is built out of cells. These are compact data structures that form a tree and make it very efficient to offload the data, deduplicate parts of the state of the system, and most importantly, create effective cryptographic Merkle proofs about any state in the system. So on top of the cells, you have types provided by TVM. And TVM is instantiated for each contract, for each message that is processed by the contract. And TVM provides you with additional types that you could work with during this execution phase. So first of all, those are integer types that make it friendly to work with cryptography and financial operations. But then there are also operations with hash maps that allow you to use lists and dictionaries based on cells inside your contracts. However, you should be aware of the costs associated with large data structures and deep chains of cells that may incur higher than usual costs on your contract execution.